Well, thanks. I'm really tickled and honored that Dave and the other organizers wanted to help me celebrate this anniversary and remembered it even. Yeah, I had no idea. I mean, I knew these things were pretty cool when I figured out that bit, but I really had no idea how much and how quickly it was going to change the field. And the thing I certainly anticipated the least was all the new connections it would open up between string theory and mathematics. And in fact, since Dave mentioned he was going to prepare a transparency, I also prepared a couple of transparencies on the connections between string theory and mathematics. The first one's a cartoon, which you may have seen before. Gary Larson, The Far Side, What We Say to Dogs, okay, Ginger, I've had it, he's out of the garbage, etc. And of course, what the dog hears is blah, blah, Ginger, blah, 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 Ginger, just her name. So I'm often reminded of this cartoon when sitting in seminars, and you can probably guess where this is going. So this is a genuine abstract. I didn't have to edit. I thought I had to edit. I didn't have to edit. This is a genuine abstract from a genuine paper. This paper describes how grow into the groups of coherent sheaves and so on. And this is what Joe hears. There is T-duality. I got that one. Anyway. So in defense of mathematics, I'm actually going to use some K-theory today. Okay, so the rest will be on the blackboard. And, oh, sorry. I should know where this is by now. I guess we can post this on the website. You can, yes.
What do we say to cats?
No, I forget that one. How's that go? Oh. Oh, not even. Okay. Okay, anyway, I'm really happy that the timing is quite perfect, that I can not only reminisce about 10 years ago, but also tell you something new. And I don't know how deeply important it is, but certainly it's something which is very surprising. And I actually want to start with cosmology. So a cosmic string is a one-dimensional object which is of cosmic size. They might span the entire visible universe, or they might be loops of, say, galactic size. And actually, string theory and its compactifications comes with a large set of possible one-dimensional objects which could be out there. There are the fundamental strings themselves. There are the D strings. That would certainly be cool. And also wrapped branes, because I'm talking here about things which we see as one-dimensional. So they could be higher-dimensional things that are wraps that we see only one dimension. Also, solitonic, that is classical configurations, strings and branes, up in 10 dimensions. But also, down in the 4-dimensional effective theory, you can have additional objects. You can have soliton strings and also confining strings down in D equals 4. Lots of candidates. In fact, thinking about the cosmological constant and the landscape suggests that our vacuum, the extra dimensions, are extremely topologically complicated, so that there might be of order 1,000 candidate cosmic strings in our vacuum, and that's not even counting their bound states, which makes the number perhaps countably infinite. Which sounds, again, real promising, but what's not important is how many such strings actually are supported by the theory, but how many are actually produced. And in order for them to be cosmologically interesting, you have to produce not only some gas of small loops in the early universe, you actually have to produce strings which are essentially infinite random walks that go on no matter how large a volume you look at, they go on. You need those infinite random walks they'll expand with the expansion of the universe, and then they will seed through intercommutation and loop formation a network of cosmic strings. And in fact, there are several ways known, several kinds of phase transition that will produce such infinite strings. And so what's important for cosmology is not the number of possible strings, but the number of phase transitions, or the number of strings that are actually produced in phase transitions after inflation, so that they wouldn't be diluted away, but soon enough after inflation that they have a high enough energy scale that they have strong gravitational effects. And so we have to hope that there's at least a few of those. But besides their being produced, it's also important that they survive from the time they're produced to today or sometime close to today in order to leave observable effects. And so that's what this talk is about. It's about the stability of long strings. And I want to propose a topological classification of long strings according to the topology that you would see, not looking inside the core of the string, but just making measurements outside. So first, local strings have no observable topology. Global strings. The global strings are the easiest to see because they have a scalar field that winds when you go around them. So if this is the endpoint of the string, let me draw it over here. This is the endpoint of the string. There is a scalar field which changes by some discrete amount, some finite amount, and so locally here there is a gradient that you could measure in some local measurement. So there's a local scalar gradient. Okay. And then there are enough Bohm strings which don't have any locally measurable properties at long distance, no gradients, but you can detect them through an interference experiment. If you send particles on both sides and look at the interference pattern on the other side, then the fringes move depending on whether or not a string is there. So there's some net, in other words, there's the string, the particle wave functions aren't periodic going around the string, they're periodic up to some non-trivial phase. And actually there's this I thought this was the whole list, but in thinking about it, you have to actually subdivide a Aharonov Bohm into two cases. The first case is that you can see the string with a neutral particle. This is assuming that if there are low energy gauge groups. So we distinguish particles by whether they're neutral or charged. Then the Aharonov Bohm string, you have a neutral probe with the what I'll call quasi-Aharonov Bohm strings. You can see them in an experiment like that, but with charged probes only. They aren't seen by neutral probes. Okay, so any questions so far?
Isn't this variety of different kinds of strings in gauge theory and string theory is also disturbing? Because suppose we see one, how do we decide if it's evidence for string theory? I mean, I know this is...
Well, that's a different seminar. That's a different seminar. Why don't we save that? Because, I mean, okay, the short answer is that different kinds of strings do different things when they collide. They can either pass through each other, they can reconnect or intercommute, or they can also, in some cases, stick and form more complicated networks. And so if cosmic strings are seen, then there'll be a period of many, many years when, okay, so it's so these, the relative probability of these different things happening feeds into the properties of the string network and therefore into the signatures. And so after a string you've ever seen, there'll be an extended period of figuring out what are the microscopic properties. Now, going from here to here, well, in the simplest case, the classic variety of string always does this. Whereas for the fundamental strings, it's a quantum process, and they usually do this. And so if you have only two models, the classic soliton strings and fundamental strings, you can differentiate them. But of course, if these are ever seen, perverse people will make thousands of models. And,
What do we do then?
Pardon?
What do we do then?
Well, we make models. But this is far enough in the future. I mean, we'll see. We'll see. Yes, right. This is a good problem to have. Thank you. Yes, Steve.
Quick question on the operand on
Yes.
I'm confused about the neutral probe part. Usually we detect operand effect with a charge.
Neutral under all low energy gauge groups. It's charged under the group which is broken, but neutral under all low energy gauge groups. Right. Mark? The global ones have a logarithmically divergent energy per unit length. All the others have a finite energy per unit length. Right. The logarithmic divergence is no problem because the relevant argument of the logarithm in cosmology is the distance to the nearest string. So the logarithm might be 100, but it's not infinity. And so the cosmological properties of these are not so incredibly different from the cosmological properties of the other ones. They're different, but not incredibly different. Okay, now, the reason for this classification is because it governs the possible decays of the strings. So for local strings, there's no topology, and so there is no protection. So the decay is breakage. That is the string, but if it has no topology, there's nothing to keep it from falling apart into dust. It can break apart into short strings by formation of pairs of endpoints, which then disperse.
Don't you need monopoles in the theory to break one of these strings?
This is just what I haven't. You're getting ahead. You're getting ahead. This is just what would be allowed according to what any external observer can see. The external observer sees. I'll explain in a second why I'm making this differentiation. It's a very good point, but I'm getting, yeah. So just based on this information, there's nothing that prevents it from breaking. Now for the global string, there is some kind of topology which you can see arbitrarily far away. So it can't just disappear because there's this scalar field gradient, but it has another instability confinement. And the point is, and this by the way, goes back to Witten emphasized this in the string theory literature. It was present in the cosmic string literature in a more scattered way before him. Anyway, the point of confinement is the following. So these have a scalar gradient. So this is the field as we move around the string. As we move around the string, you have a scalar field that increases from 0 to pi. And there is some gradient energy cost for that, which is this logarithmic divergence that Mark asked about. But in string theory, we very strongly believe that this picture isn't possible. So what is it? Sorry, the point is the following. So let me plot here in the vertical direction the potential as a function of phi. This picture is not possible. That is, you cannot have physically distinct gauge and equivalent vacua which have exactly the same energy. You could if the world were supersymmetric, but the world is not supersymmetric. And what we know about string theory says that there is always some symmetry breaking effect. You never have an exact global symmetry for which you have a Goldstone direction. There will always be some symmetry breaking effect, perhaps an instanton, that raises the potential, that makes it non-trivial. So now when you walk around the string at long distance, you're paying not only gradient energy, but potential energy for going around the circle. And so the energy is not logarithmic divergent, it's at least linearly divergent. And the effect is that the strings don't grow large, they collapse. For a finite loop of string, the effect is that there's a linear confining force due to this potential energy that makes it collapse when it becomes smaller than the horizon size. It's a little less clear why the so there's there's a domain wall. The domain wall represents the part of the region of space where the field is going over the potential. There's a domain wall which pulls the string and makes it collapse. For an infinite string, it's harder to imagine how it could just disappear by this process. So there's some domain wall attached to it, which wants to pull it. But in fact, you never have just one string. You always have the string and a gas of loops, which become holes in the domain wall. And so what happens is you can think of this not as an infinite, you can think of this as consisting of strips of finite width. And as soon as that width is less than the size of the horizon, these strips will collapse that way, and the entire network will disappear. So with global strings, the problem is that they have not just a scalar gradient energy, they have potential energy, which confines them and makes them collapse too soon to be seen. Okay, Aharonov-Bohm strings are stable because now they don't have either of these problems. They have some topology which is visible at long distance, so they arbitrarily long distance, so causality prevents them from just disappearing, but they have no actual physical degrees of freedom at long distance to have energy. They're locally, the local fields are trivial, and so these are stable. And these last ones, again, are kind of funny. Again, what happens is, if you have one of these quasi-Aharonov-Bohm strings, then if it can only be detected by charged probes, there is some flux tube built entirely out of low-energy gauge fields. So this is low-energy magnetic flux. And which has the exact same Aharonov-Bohm phases. So if you can't see it with a neutral particle, you can figure out that by looking at examples that you can always fool a charged particle by replacing the quasi-Aharonov-Bohm string with a magnetic flux tube, which also produces non-trivial phases as you move around it. And so now again, there's no topological argument that would prevent this from turning into this. And once it's become low-energy magnetic flux, it can just disperse. It can just spread into diffuse fields. That's kind of the trickiest one. And the process, by the way, by which you go from here to here is actually a local breakage process. The string breaks open, flux appears, and it turns into this. Anyway, this is the least interesting. I mean, it's the most complicated case. You don't have to think about it too hard for the purpose of this talk, but it's necessary to be precise about things. So if you have, these are actually, again, unstable to breakage. They can break. They don't immediately disappear. They turn into these flux tubes made out of massless fields, and the massless fields, just since they're massless, can just disperse and turn into diffuse fields. Okay, so let me give some examples and answer Gary's question. So the first example is the Abelian Higgs model. So we have a U1 field and a scalar field phi of charge 1 and a potential that breaks the symmetry. So the potential looks like this. And so this system supports Aharonov-Bohm or, I'm sorry, no, excuse me, Abrikosov flux tubes or Nielsen-Olson flux tubes, in which as you go around some string, the Higgs field has a non-zero VEV, but its phase is undetermined by the potential. So as you circle the string, the field winds once around the minimum the ring of vacua. So as you circle the string, the Higgs field winds once around the minima, the ring of minima. Therefore, it must be by continuity that somewhere in the middle there is a zero or a line of zeros of the Higgs field, and so there's potential energy in this region. And so there's a string there, and it's topologically stable because, again, this winding is visible out to infinity. This winding is present out to infinity. It can't just go away. Also, in this theory, there are no massless degrees of freedom. There's a Higgs mechanism. The vector potential and the Higgs combine into a massive field. And what that means is that all local gauge invariant quantities fall off exponentially as you move away from the string. So in particular, while the scalar field has a gradient, its covariant derivative is 0. That implies that the vector potential also has a line integral around that circle, and therefore by Stokes' theorem it implies that there's a magnetic flux in the core. The integral of the magnetic field on that plane is, in these units, 2 pi, in order that the Higgs field can be covariantly constant as you move around. Sorry, that picture is kind of ugly, but anyway, so it's a zero the Higgs field, and so the Higgs field has a defect in it, and also the gauge field, there's flux running up the axis. So this is a local string by this classification. This is a local. I should say there's a conjecture at this point. The conjecture is that in string theory, every decay allowed by this classification actually happens. That's the conjecture. The conjecture is that in string theory, anything which is not forbidden is required. Yes. Anyway, and so the conjecture is that when any one of these decays is allowed by the topology, there'll be some process by which it can happen in string theory. Now, so we come back to this example here, the Abelian Higgs model, and it's a local string because, again, at long distance, the gauge invariant fields all fall off exponentially, and there is no Aharonov-Bohm phase because the only possible probe particle is the Higgs field itself, which has charge 1, and that's periodic going around the string. So this is a local string. But it's also absolutely stable because there's no way that it can break. It has a topology. And so this shows you that in general quantum field theories, my conjecture isn't true because I have a stable local string. Okay, so what's the point? Well, the point is the following. Whenever you see an abelian, a U1 gauge symmetry at some scale, your prejudice is that at higher energy, it's going to be part of some more unified structure, like a semi-simple group in granularification, or maybe unified with gravity in Kaluza-Klein theory, or sort of all of these things at once in string theory. And just one quick aside. I'm not going to talk much about global strings, but the simplest way to make a global string, same model without the gauge field. And now you have the same scalar field configuration. It's stable against small perturbations, but now you have a real gradient, a physical gradient at long distance. Anyway, that's just an aside. But coming back to this case, your prejudice is that whenever you have a U1 gauge symmetry, it's going to be part of a larger structure. And so we add a monopole with So this is the flux. So we add a monopole to the earlier model with the minimum charge allowed by the Dirac quantization. And now we see that if we have a long flux tube, it can break. The flux can end on a monopole and start on an anti-monopole. And also there was this Higgs winding, but in Dirac's description, the monopole has a Dirac string, a singular gauge transformation sticking out of it, which just exactly undoes that winding. So there's really only vacuum in between. So if we have this theory and we realize that it should be unified and that there should be in the spectrum monopoles, then in fact the string is not ultimately going to be stable. And so that's the point of this classification. It's, the usual classification of solitons would call this stable, but this is sort of a classification taking into account possible embedding into a more complete theory.
Suppose the unification scale is really, really high.
Okay, good. So if this were really a cosmology talk, then I would have to talk about for the decays that can happen, their rates. And indeed, in many cases, what may in fact save cosmic strings as a, what may in fact make cosmic strings only possible is that some of these decays which are allowed are slow, and that can easily be the case. But since this is a math talk, I'm only concerned about topology. Things can either happen or not happen. Rates don't matter. And so for the purpose, and there's a reason, for where I want to get to with this talk, I really only want to ask possible or not possible and not about the rate. It's an important question. It's a vitally important question, but I'm leaving cosmology behind now. Okay, so, yeah, in fact, just to go on with that question, it's very simple. If the scale of the monopole mass is a factor of 10 or more, the scale of the string tension, then these things will be stable on cosmological timescales, which is not a very large, not an especially large hierarchy of scales. So in fact, there's a good chance. I mean, the possibility of cosmic strings is moderately robust. Yeah. But we're talking about absolute stability, and so you see the point that I'm trying to classify things by stability even under embedding in a more complete theory. Now suppose instead we add a monopole with not one but some larger number of units of flux. So larger integer. Now the strings can't end because they have flux 2 pi. The flux in their core is 2 pi, but the flux can only end in units that are larger than that. And so instead what you have is that the monopoles become junctions. So there's the monopole, and you have Q sub m strings going into it. And so all of their flux can be eaten up by the monopole. So in this case again, the strings are stable because again, one string can't break. The strings are stable, but they're still local. Adding monopoles in this way doesn't change the classification because in particular the monopoles don't feel the magnetic flux. They aren't interesting in the RNF Bohm experiment. So one more thing. Suppose in addition to 3, okay, so 3, the problem is the theory 3 is still not complete because the Dirac quantization is not saturated. The charge of the Higgs times the charge of the monopole isn't 1, it's some larger integer. So let's think of again a more complete theory. We take 3 plus electric charges, an additional field, 1 over Q sub m. And now, again, the Dirac quantization is saturated. And now where does it appear on our list? Well, now this is what I called an R-enough-Bohm string, because these particles pick up not a phase of 2 pi going around the string. They pick up a phase of 2 pi over q sub m, and so they pick up a non-trivial phase. You can detect the string in an R-enough-Bohm experiment using these particles, and not surprisingly then, it's a stable R-enough-Bohm string. Now, so far, we only have one gauge field, and it's massive due to the Higgs mechanism, so there's no issue with the quasi-R-enough-Bohm. I won't go through it because there are more interesting things to talk about, but if you can easily make a model with 2 gauge fields, one broken, one not, and it's described in the paper that just appeared on the web. You can easily make an example of a quasi-R-enough-Bohm string, and you can see that it's unstable for the reason that I said. So what you see is that in the cases where the Dirac quantization is saturated, where the minimum electric charge times the minimum monopole charge is the minimum that Dirac would allow, this classification is true. There is always a decay mechanism for the string if this requires it, if this allows it. So it's conjectured that in string theory, the Dirac quantization condition is always saturated. It's not proven. Seems like something that a unified theory should do. It's one of the nice things about string theory, in fact, that, say, as compared to supergravity, it has a complete set of charges. But actually proving it on a case-by-case basis is hard. There's an early paper by Wen and Witten showing it for Calabi-Yau compactifications for a certain class of monopoles, and it's a very topologically complicated argument. In the case of the D-Brain paper of 10 years ago, the one actual calculation in the paper was to show, in fact, that the magnetic charge times the electric charge of D-branes was equal to 1 in the units of the generalized Dirac quantization. There was a period of time when it was pi root 2 and other values, which is why the paper appeared October 5th and not, say, a week earlier. But on October 4th, it reached 1, and out came the paper. Happily, it still is 1. Anyway, so it seems to be true that in string theory, the Dirac quantization is saturated with the minimum charge, but there's no general proof. And so that's sort of the first half of my talk. And so what I want to do in the second half of my talk is to consider a case where this assumption that any decay that is allowed will happen seems like it must be wrong, and then argue that in fact it's right. So let's see. The heterotic string. So Witten, back in 1985, considered the possibility that fundamental strings might be cosmic strings, and showed that for several reasons the heterotic string was unsuitable. But the one which is immediately relevant here is the fact that it's a global string. You have a string, its world sheet is 2-dimensional, and it couples to a 2-form field. And when you drop down to d equals 3 plus 1, you compactify, then a 2-form is really the same physics as a scalar. Its field strength is a 3-form, which is dual to a 1-form. And these are the same physics. You're just interchanging the field equation with the Bianchi identity. Also, since the string couples sort of electrically, it couples to another coupling to the magnetic field, to the B field. Under this duality, it means it couples topologically to the scalar field, and so the scalar field winds once. It's a topologic, it winds as you go around the string. So Witten argued because the heterotic string couples to a 2-form field, you compactify to 3 dimensions, it's a global string. There's a long-range gradient energy, and therefore instantons will generate a potential for this field and confine the string. Now, Witten wrote a very large number of papers in 1984 and 85, and so he seems to have forgotten that a year earlier he wrote a paper in which he pointed out that not every compactification of the heterotic string has, in 4 dimensions, a B field. In particular, in theories that have anomalous U1s, or they're called pseudo-anomalous U1s, the B field gets massive. Anomalous U1. So what's the point? What's the point? So we have some 3 plus 1 dimensional compactification to string theory. And what can sometimes happen is that there is one U1 gauge symbol. You can only have the one, such that there's an anomaly. That is, such that the sum over all left-handed fields, left-handed fermions, of the charge cubed is not equal to 0. That's an anomaly. Now, there also, in this case, will be mixed anomalies involving this U1 and the other gauge fields, and also gravitational anomalies involving this U1 and gravity. But they actually just go along for the ride. We can focus on this. But what this means is that there's an anomaly. Let's say the path integral measure isn't 0. So under a gauge transformation, for this anomalous U1, the path integral measure is not invariant, but changes by a phase. And this is bad, because the theory is then sick in some way or another, if you have a gauge symmetry that has an anomaly. But string theory is wonderful and doesn't do sick things, and so it saves you by what we used to call a string miracle. Namely, there is a canceling effect in the theory. So what happens is you have, again, the same two-form field that I was talking about. And in heterotic string theory, this transforms under gauge transformations as follows. You can see this from many ways. It was originally derived from supergravity. It follows from a worldsheet analysis. And this is a tree-level effect in string theory. And again, to keep things simple, I'm including only the one U1 gauge field that is participating in that is essential in the discussion, and I'm leaving aside all of the constants that should appear there. But now there's also a one-loop term. There's also a one-loop term. This is still in 4 dimensions. The integral is B wedge f. And what you see is that when you combine this, so this is the 4-dimensional projection of the 10-dimensional anomaly cancellation of Green and Schwartz in these compactifications that seem to give you an anomalous spectrum. Then you also acquire at one loop just the right term so that the transformation of the B field generates a term in the action that cancels the anomaly from the fermion measure. And again, this work when this automatically happens for this gauge, for this anomaly, and for all of the mixed anomalies and the gravitational anomalies at the same time. That's why we called it a superstring miracle. Okay, any questions? Okay, so what's the point? Well, the point is that you have this term induced at one loop if and only if there's an anomaly, and that's a mass term because there's no derivative on B. This mixes the two-form B with the gauge field A, and it makes them both massive. In fact, it's just the usual. It's exactly the usual Higgs mechanism if you write it not in terms of B, but in terms of this equivalent scalar. And so exactly when there's a U1 anomaly in low energy theory, the B field is Higgsed, and it's no longer in the spectrum, and so the heterotic string can't be a global string. And when you look through various compactifications, in fact, it can be any of what I listed. It can be local, it can be a Aharonov-Bohm, or it can be quasi-Aharonov-Bohm. And that means if this conjecture is true about stability, that it should be able to break in these compactifications. But also, since these compactifications, so there should be some mechanism by which the heterotic string, this is down in the three-dimensional picture, can end on something, and then by breaks and whatever appears, and the anti-thing appears over there. This is in 3+1, but these compactifications have in general, well, in the simplest case, they have an arbitrary size for the compact dimensions. So you should also be able to expand them out and see this same picture in 10 dimensions. You should be able to see a heterotic string in 10 dimensions just ending on something. Now, how can that be? Well, why is that a problem, first of all? The reason it's a problem, the reason that we didn't have open heterotic strings a long time ago, is that on the heterotic string, well, because it's heterotic, you have 8 supersymmetric fermions moving one way. That's, say, in a physical gauge. Otherwise, it'd be 10. And there's 32 gauge fermions moving the other way, and there's no way to put consistent boundary conditions on these fields. You can contrast that with the type 2 string, where you have 8 fermions moving one way and 8 fermions moving the other way. And so when they get to the endpoint, they just reflect. And depending on whether you're in 2A or 2B, they reflect in just such a way that corresponds to ending on a D brane of some dimension. So here's a very natural boundary condition. Here, well, it's pretty obvious there's no boundary condition. You have more degrees of freedom moving one way than the other. So here we have this so if the conjecture about stability is true, then we should be able to have a picture like this. But now we have this problem that we have 32 fields moving this way and only 8 fields moving this way. And so how can that happen? What happens when they reach the endpoint? Okay. Before we answer that question, let's answer an easier question, which is, when a string has an endpoint, then we have to worry about the gauge invariance associated with the B field. What we have is that delta of the integral of the world sheet of B, so B is a gauge field, delta B is D of something, and so this becomes the integral of the boundary of alpha. And so if a string has an endpoint, then this gauge invariance is violated at the endpoint, and that's bad. But there's a well-known way to fix that. So we have to cancel this variation against some other variation of another term in the action. And in particular, we're looking for a term which is built out of the potential B and not out of its field strength dB, which is invariant. And there's one such term. It's the 10-dimensional lift of the anomaly cancellation term. It's the integral in 10 dimensions of B wedge trace. This is for the SO32 string. I'll have to talk about the E8 string separately for a reason to be explained. F, wedge F, wedge F, wedge F. Okay, so there is a term in the action which would also have a variation under a gauge transformation. And normally it's invariant because delta B is D alpha, and you move the D over here by parts, and it kills that, and so this is normally invariant. And it will not be invariant precisely if there's a generalized monopole, a source for this. If at the endpoint if on an H sphere surrounding the endpoint of the heterotic string, this is up in 10 dimensions now. We're lifting the picture. We're going to discuss 10 dimensions first. If up in 10 dimensions on an H sphere surrounding the endpoint of the heterotic string, there's a non-zero value of this thing. So this is like instanton charge, which is two F's wedged together in 4 dimensions, but it's up in 8 dimensions. And there's a fair literature on this, and in fact there have been various applications to the heterotic string, including by Pierre and Ruben, who are here or soon to arrive. But I'm pretty certain that it's never been applied in this case to open heterotic strings. In fact, the simplest way to check this was to do a Google search. I searched on, quote, open heterotic, end quote, and on the entire web, I got 2 hits. One from biology, which is where heterotic energy came from, and the other was one of these sites that has long blocks of random text, just to entice search engines to glom onto it. So now there's a few more. Apparently there's like 10 hits to the KITP website for this talk. But anyway, so apparently there has been no application of this to open heterotic strings. But okay, so the first problem, which is totally standard, whenever a type 2 string ends on a D brane, you have the same issue, and you again restore the invariance by having some field emanating from the end point of the string. For a D string ending on a D brane, it's simpler. It's the integral of just the dual to the electric field strength of the string. But here it's this thing. Okay, so we first solved the easy problem of how do we retain the two-form gauge invariance if the heterotic string ends. Now the hard problem. Okay, so there's something funny about the fields in space-time in this situation. So there's, in the heterotic string, a gaugino that couples to this gauge field. And so it satisfies the Dirac equation. So a radial part, time, radius, and angular part of the Dirac operator. And what you see is that precisely if the angular part of the Dirac operator, the part on the 8 sphere, has a 0, then what's left is basically a 1 plus 1-dimensional Dirac equation. The fields, it's like an S wave. The fields simply move outward or inward depending on whether this product, whether gamma T, gamma R is plus 1 or minus 1. And what the Atiyah-Singer index theorem says is that the net mismatch between the number of zero modes moving with a plus sign here and the number of zero modes with a minus sign here is just the integral over the 8 sphere of trace f wedge f wedge f wedge f, the same thing. Okay, so what this means is that when you solve for the mode expansion of the fields in space-time, there are more fields moving into the endpoint than moving out, or vice versa. Now this has appeared before in physics. If you add magnetic monopoles to the standard model, as you expect will happen in a grand unified theory, the same thing happens, as was pointed out by Rubikoff and Callan. There's not a mismatch of the number of ingoing and outgoing modes, but a mismatch of their quantum numbers. You will find modes that carry baryon number moving in, quarks, and modes that don't carry baryon number, leptons, moving out. And so what this means is that a magnetic monopole added to the standard model will catalyze baryon decay, not with a grand unified cross-section, a tiny cross-section, but with a strong interaction cross-section, because that's what governs the range of this effect. This is pretty cool. It was one of the advantages of having been around a while is that you remember these things, and this was explored in the early 80s, and it seemed to work, but it was been put on the shelf until the magnetic monopole is found. Anyway, so in the standard model, a similar effect will cause a monopole to catalyze baryon decay. Here, okay, well here you now see what the whole picture is. We have let me make room for it. We have a problem on the world sheet that there are more fields moving to the right than to the left. And we have a problem in space-time that there are more fields moving outward than inward. And when you work out the index, because it's the adjoint representation of the gauge group, the Casimir is 24. And at the other end. So this is a very funny kind of string where the endpoint, where the boundary condition of the endpoint is not that the modes that get to the end reflect. Some of them reflect. 8 of them reflect. 8 of them reflect. And the other 24 just pour out into space-time. So they pour in one end and pour out the other.
It's a wormhole.
Well, no, it's more like a wire. You know, it's yeah.
I talk to somebody.
Well, if we lived on a brain and the string went off the brain, then maybe it would look like a wormhole. You probably, I wonder. Okay.
What's the
Yeah.
Wolfson description of this number?
I'm sorry?
What's the Wolfson?
Okay, we'll come to that in a second. I just want to say that if you take a particularly symmetric choice for this gauge field, then by symmetry alone you can kind of pair up 8 and 8 and 24 and 24. But anyway, I think this is pretty convincing that this happens. It's complicated though, because indeed this is not a new perturbative string theory. This mixes up levels of quantization because we have the first quantized modes on the world sheet have a boundary condition which relates them to the second quantized modes in space-time. Steve?
So you have a finite energy configuration?
I'll come to that in a second. The energy is interesting. But it's not something that has a perturbative description. It's outside the technology of perturbative string theory. And but of course, lots of things are outside the technology of perturbative string theory. I think it's pretty compelling that this picture is right, but we can do something a little bit better using this K-theory business. So if we S-dual, sorry, over to the type 1 theory, then the heterotic string becomes a D1 brane, and the vacuum over here is full of D9 branes, and this becomes a D1 brane ending on a D9 brane. And now over here, where these are D objects, we have a nice picture due to Sen and Witten in particular for constructing any possible object, which is the following. The type 1 vacuum has 16, actually 32 before you project D9 branes. But you can add any number of D9 plus D9 bars, which are unstable, discussed first by Mark Srednicki. They have a tachyon field, but the point is that the possible extended objects, the possible D objects in this theory can all be understood in terms of topologically non-trivial configurations of the tachyon field on the D9s and D9 bars. So to construct this object, I want to actually just look at a subsector, and the rest will just go along for the ride. Again, this K-theory stuff is stable against embedding in sort of larger sets of D-branes and anti-D-branes. And so the tachyon field here, which is a string which stretches from here to here, is therefore a 16 by 8 matrix, which is sort of the 8 by 8 identity. That gives the vacuum, and 0 down here, and then any rotation of this, any SO16 rotation of this. So what we have to work with is this vacuum and its SO16 rotations. And if we think about, I want to think about this as, well, if you think about this, this is a 16 by 8 matrix. You can think about this as a map. If you multiply it by a column vector over here, you can think about this as a map from R8 into R16, or since it preserves norms, you can think about it as a map from the 7 sphere into the 15 sphere. And we now want to talk about what the tachyon field does as we move around the 8 sphere surrounding the endpoint. So what we have is a map from S8 across S7 into S15. And there is a famous map called the Hopf map, the fourth Hopf map, in which this times this, it's actually a bundle. It's a non-trivial map. It's an S7 fiber over an S8 base, which exactly covers the 15 sphere ones. And it's kind of the last example, apparently, of being able to construct a higher dimensional sphere out of lower dimensional spheres in this way. So we're going to let the tachyon field be equal to this Hopf map. So as we move around, so there's an actual formula. I'll give it to you. T is Anyway, the formula doesn't matter so much. But it's a non-trivial bundle, of course. The 15 sphere is not just a product like this. So what that means is, as I look on the 8 sphere here, there's a point where the tachyon field becomes singular, and as I move out from the origin, I hit that point here. So there's a singularity which moves out from the origin along one axis when I have this tachyon field. Now, I don't want a singular tachyon field because I really want to describe physical configurations of a smooth tachyon field, a function in this whole topologically trivial space-time. So I don't want to use exactly this thing. I want to smooth it near this axis where it's singular. The axis is the positive x9 axis. I should have gone going the other way. So just multiply it by a smoothing function, which is sort of 1 out here and drops to 0 in the core. So now we have a smooth configuration of the tachyon field, which has some kind of one-dimensional object, which ends, and then some kind of smooth configuration around that point. And in fact, the smooth singularity near that axis is exactly the K-theory description of the D string. So this tachyon configuration describes, in fact, a D string ending and turning into a smooth configuration. And it's exactly then what? It's exactly the dual to the ending heterotic string. Now, it's conjectured that you can really use this as a construction of string theory, that you can do string field theory in this enlarged space, and it really defines the theory, at least perturbatively, and so it actually provides a construction of this object and not just a plausibility argument. I also think it's very likely true that, although I don't know much about heterotic matrix theory, but it would seem like if you tried to use matrix theory as your non-perturbative construction of the heterotic string, then this construction would probably embed in that in some plausible way. Yes? Yes? Here?
First, the anomaly polynomial contains a double piece, which is the double trace part.
Yes?
Configuration, the double trace part doesn't contribute.
Doesn't contribute at all. That's right.
What I'm saying is that
Right.
you are getting the energy of the D1, extension of the D1 string from the single trace part, and this is the K-theory analysis. Actually, with Goodman and Sampson, what we showed is that if by looking at calculations, taking into account the double trace part, we got the worksheet action for an heterotic string. We looked at
The double
configurations.
So you showed it had the right degrees of freedom to be a heterotic string.
Yeah.
Yes. Yes.
Except that we are in a specific pattern because we have this SOA pattern, so you have to combine it with this configuration. But we got the worksheet as well of a heterotic string. So it's picture that you are describing.
There is this question of energetics that Steve asked about, because in fact for this configuration, Well, okay, so the fact that this has a non-trivial integral over the 8th sphere means that F falls as 1 over r squared. And so the energy density, which is F squared, falls as 1 over r to the 4th. So this is like a global string in the sense that the energy density falls to 0 at infinity, but we've got to integrate that over an 8th sphere. So we have the integral of r to the 8th dr over r to the 4th. So the energy does diverge in the infrared. The energy density is finite. And, in fact, in cosmology, you have available a finite energy per unit volume. So you can make things like global strings that have infinite energy. Although in this case, this is probably unstable to some kind of angular mode of decay. However, we're topologists. We've never heard of energy. The only question is, this is a configuration which is topologically allowed. It's in the space of states, but it's not dynamically stable. And it's worth thinking about those things. In fact, again, it comes up when you think it's important, obviously, for cosmology. So up in 10 dimensions, a heterotic string could not break. Up in 10 dimensions, a heterotic string could not break because the endpoints would cost infinite energy, or they would cost some energy which grows rapidly as you try to pull them apart. So I'm out of time, but now when you compact, so we first deduced, though, such a thing should be possible by thinking about these pseudo-anomalous compactifications. And in those, the divergent integral is cut off by the volume of compactification. So in those compactifications, in fact, the endpoint of the heterotic string has finite energy, and those compactified heterotic strings can really break. Dynamically and not just topologically.
What about E8 cross E8?
So finally, E8 cross E8. So this is really funny, but in E8 cross E8, there's this thing that the trace of there's no quartic Casimir. The trace of the 4th power of f is equal to the trace of f squared, and that therefore it vanishes when integrated over the 8th sphere. The reason is because this is closed. D of this is 0. On an 8th sphere, there's no non-trivial 4 forms. So this is D of something. And then we can move the D over by parts, and it kills that. So an 8th sphere cannot support this double trace topology. And so you cannot make an E8 cross E8 string break. Yes? What about T-duality? So the simplest way to show that this is all nonsense, then, is to take your SO32 string, put it on a torus, and turn on an appropriate Wilson line as described by Narayan and Ginsburg and make the torus small. However, as soon as you put the heterotic string on a torus, it becomes a global string, and it can't break. I believe you can't make a contradiction in this way. And I haven't had time to talk in detail about the compactifications, but in fact, I believe that if you consider any smooth compactification of the E8 cross E8 string, the heterotic string will always be a global string. There'll always be an axion visible at long distance. For the SO32 string, you can actually realize any of the 4 types of string. And so in that case, in some cases, it can break. Okay, so there's the surprise. We learned 10 years ago that type 2 strings could break, and it was obvious that heterotic string couldn't break, and now it seems that under some circumstances they can break. It's not clear that in any sense, from the point of view of the heterotic string, this is more like a Neveu-Schwarz, over in the type 1 theory we have D9 branes. So by S-duality, this is more like Neveu-Schwarz 9 brane, something that Chris Hull has talked about. It's not clear that this has anything, much more than curiosity value and any broad significance, but certainly surprising. As coming back to the cosmic strings, Witten listed several reasons why the heterotic string couldn't be a cosmic string. Another was that its tension is too large. In its tension is close to the Planck scale, and we've now learned that through warp compactifications and compactification with branes, you can lower the tension of the type 2 string. I still don't know of any strategy for lowering the tension of the heterotic string to a level where it would be phenomenologically interesting. But of course, I started my talk with a long list of possible strings, and the heterotic string certainly has several other candidates. Okay, so I think it's a good place to stop. Thank you.
So these instant Helmholtz configurations for this integral and the force is not zero. So can that take any integer value or something like that?
Yeah, it's quantized. It's got an integer quantization, right? It's
different types of endpoints. I mean, the heterotic string always ends on one where that integral is 1 or something.
The integral is 1 in the vector representation and 24 in the adjoint representation. That's why there's 24, and that's the minimum. That's the minimum quantum. It's also the quantum given by this construction.
But you can have junctions. So if you take a higher,
you could have. Well, so when you compactify, you get many cases where there are junctions. Up in 10 dimensions, I don't know if the multiple chart, well, they're all unstable because the energy is infinite. But as soon as you compactify, the energy is finite, and then you have various possibilities for junctions.
Can you say more about the description of the F configuration?
I mean, I can write down a formula for it. It just sort of it's the thing which makes this thing covariantly constant. And so it's something that can be written down in terms of these are the SO16 gamma matrices acting on the 6. You write down a formula for it. It's not uniquely determined. I mean, there's an obvious spherically symmetric one, which is probably unstable in terms of turning into something up in 10 dimensions is unstable to making something more string-like. But again, as soon as you compactify, it becomes stable because you cut this off and you have a finite energy endpoint.
So part of your argument was that anything that's not forbidden must happen. And you managed to build us an SO32 string, even which ends, even though we would have thought that you couldn't do that.
Right.
But you didn't manage to find such a thing for EA cross EA.
And as I said, in terms of, again, like I said, that original classification is based on what the string looks like in 3+1 dimension, or in 3+1, for the parochial reason that our part of the multiverse has 3 large dimensions. And in that classification, the E8 cross E8 string is always global when you compactify it. And so it's consistent that it can't break. Yeah. It's interesting. I mean, as you go through things in a case-by-case basis, every case is different. I mean, as you see here. But so far, there are no exceptions to this conjecture.
I mean, maybe it ends at a singularity, though.
Sorry?
Maybe it ends at a singularity.
It could end at a singularity. Yes. Because if the singularity had a 4-dimensional, was a cone like with a 4-dimensional base, then it could end. Yeah. It can't end on a smooth. It can't end at a smooth point in space.